Welcome back. Thanks for coming back from break. Just to review where we left off computation here. Remember, we started the entire discussion by asking the question, can computers solve anything, right? And even to begin to answer that question, we had to translate it into something that made mathematical sense. And so, can algorithms solve problems? We translated that into Turing machines decide languages. We went through and discussed what languages were, that they are subsets of finite binary strings, what Turing machines are. There are these devices that have this finite state control, this input tape, and then this infinite output tape. And to decide a language means that on any input, it'll do some computation, it'll halt, and then it will either accept or reject that input, depending on whether or not that input is in the language. A Turing machine does not decide a language if it gets stuck in an infinite loop. Okay, and so we were able to ask the question: can any problem be solved by a Turing machine? Can any problem be solved by an algorithm? And we showed two proofs that that's not the case. Cantor's diagonalization proof showed that that Turing machines are countable, but that languages are uncountable. And so already we know that there are languages that are not decidable by any Turing machine just by using this 150-year-old Cantor's diagonalization proof. Just like there are infinitely many more real numbers than there are, say, integers. And then we actually gave an actual problem, like the halting problem. That given a Turing machine and given this input, does this Turing machine halt on this input? That problem is not solvable by any other Turing machine. And so there are some problems that are undecidable by any Turing machine. Translating that back into our original language is that there are some problems that are unsolvable by a computer or unsolvable by an algorithm, okay? So we did finally answer that original question that started this entire discussion. What I want to do now is I want to turn our attention towards more, not practical applications or anything like that, but more practical or questions that you're already familiar with. Computational complexity, right? So given an algorithm, you can analyze its complexity using, big O analysis. For example, selection sort. Right? Selection sort is an algorithm that sorts an array or sorts a collection. What is its complexity? Do we all remember? Order what? It's really bad. And so it's not exponentially bad, but it is n squared, right? N squared. Versus, say, quicksort, right? Which in best case or average case time is going to be order what? N log n, right? So those are two algorithms that solve the same problem. We need to make sure that we have a distinction between what an algorithm is and what a problem is. Both of these are algorithms that solve the sorting problem. Right? So you can have multiple algorithms that solve the same problem. But you can also have different problems, and you need to make a distinction between those problems, right? So first of all, though, what does big O analysis mean with respect to Turing machines? For Turing machines, we have measures of time and space, right? For a Turing machine, time is measured by the number of transitions from one state to another for a given input before it halts and accepts or rejects. Now this kind of captures the intuitive notion of what we mean when we mean, time. Think about a computer. A computer actually, goes through CPU cycles. So one cycle, right? It's doing these updates. It's executing some sort of instruction. That instruction might take one CPU cycle. It may take 5 CPU cycles, whatever. But the basic unit of measurement for a computer, for a processor, is a cycle, right? How many things can it do? And that's the same for a Turing machine. A Turing machine has a current state. It's looking at the input. It's looking at the output. It makes a decision on which state to go to next. Right? Memory is measured with respect to the amount of work tape used in the computation of an input. Right? So memory is the same thing, right? If you're writing 1 bit, if you're writing 2 bits, if you're writing 3 bits, however many bits you're writing to RAM, that's the same thing as writing to the tape memory in a Turing machine, right? The input size of a Turing machine is the number of bits in the input tape, right? Tape. There we go. So if the input is x, then we write that that the length of x is equal to n, right? So this is the length of x, the input x. Don't ask me why. I think it's kind of like cardinality. That that notation, the magnitude, right? If you're looking at it with respect to like the norm or something, the absolute value, we just use the same notation there to denote the number of bits in the input, right? So it makes sense. It makes sense to bound a Turing machine just like an algorithm. So for example, you can say that the time t sub n is going to be order of f of n, where f of n is some function, right? That is a time bound on the running time of a Turing machine. Right? So this makes complete sense, and all we have to do is take everything we know about algorithm analysis and move it over to a Turing machine context, right? This allows us to define complexity classes. Right? Complexity classes are defined with respect to problems, right? Note, big note, right? Complexity classes are with respect to problems, not algorithms, right? Algorithms are proof that a problem lies within a complexity class, right? Not that you don't say that an algorithm is in a complexity class. You say that a problem is in a complexity class because you came up with an algorithm. So to understand that, let's actually define our first complexity class here, right? The complexity class deterministic polynomial time, denoted as, now here's where I'm going to have to start cutting and pasting some here, because I'm not going to do the math serif font every single time. There we go. All right. Denoted as P is the class of all problems such that there exists a deterministic Turing machine, TM for short, deterministic, get that right too, Turing machine that decides the problem. Right? So in other words, languages. P, and let me cut and paste this now. P is the set of all languages that are decidable by a deterministic Turing machine that runs in polynomial time. Right? In other words, f of n, that time bound there, f of n is in or big O of n to the k for some k. Yep, that renders correctly. Okay. So for example, what about sorting? Where does is sorting in P? Or why? Is the sorting problem in P? Yes, because the existence of an algorithm proves it, right? The existence of either selection sort or quick sort proves that you can solve the problem in polynomial time by a Turing machine. By a Turing machine, we of course mean an algorithm. Existence. There we go. Polynomial. Come on. Polynomial time. There we go. What about some other problems? So for example, the 0-1 knapsack problem. Is that in P? Do we know or not? Do we have a polynomial time algorithm for it? What about the one that you programmed for your last homework? Right, that was a pseudo polynomial time, right? Yeah. So who knows? Who knows? No one, right? Has come up with a polytime. Here, I'll shorten it to polytime algorithm for it yet. Right? And likely they're not going to, as we'll see here in a short while, right? So we've got some things in P, we've got some things not in P. Another complexity class would be exp, let me go ahead and write it exp. Yeah, go ahead with a question.
So it's like is there like a huge difference between exponential and polynomial?
Oh yeah, exponential. Another complexity class would be exponential time. And so what would that be? Are all languages decidable by a Turing machine that runs in exponential time? Exponential time, right? For example, f of n now is not in big O of n to the k for some k. It is big O of 2 to the n. There we go. Right. So now, another question. Is the sorting problem in exp? Question mark? Yes, for the same reason. Why? If you've got a polynomial time algorithm, you have an exponential time algorithm. It's a big O analysis. Remember, it is the worst case running time. Is the 0, 1 knapsack in exp? Also yes. Why? What's the algorithm that you ran on homework 1 for this problem, or maybe 2 for this problem? Right? It's the brute force, right, where you generated all possible subsets. How many possible subsets are there of n elements in a knapsack? 2 to the n. Right? So yes, you have this relation. So my first observation is that those two complexity classes are contained within each other. Subset equal x. Right? That's not what I wanted. I wanted this. Sorry. There we go. All right. So P is a subset of X. All right. Those are sets of languages, right? So keep in mind that these complexity classes are sets of languages. And so it makes sense that you can talk about subsets. Anything that's solvable in polynomial time is, of course, solvable in exponential time. Are there things that are solvable in exponential time that are not solvable in polynomial time? Yes. Proving that goes beyond the scope of what we're going to do here, though. Okay? We don't know. So that's going to introduce yet another complexity class here based on what's called nondeterminism. Right? So non-deterministic computation. Right? So it's a theoretical model of computation. It's a magic. Think of it as magic. Okay. The non-deterministic computation it's not randomness, right? It's not a real computational model. It is a theoretical model, a magical model, right? It's a mathematical model, right? Non-determinism is a theoretical model of computation. You cannot build a non-deterministic computation machine in real life. You can build a quantum computer in real life. People have not very big ones, not scalable ones yet. Possibly, it's not even going to be possible to have a general purpose quantum computer. Maybe not even within our lifetimes. Who knows? But that is an actual real model of computation. Of course, we can build real computers. They're deterministic computers. There's no way that you can build a non-deterministic model because it's completely theoretical, right? It works, determinism works in 2 phases, okay? It has a guessing phase, right? It guesses a solution to a given problem non-deterministically, right? So it just guesses, right? Again, it's not randomness. You could use a random coin to generate solutions, but that's randomness, all right? Then it has a verification phase, okay? Given the guess, it verifies if it is a valid solution or not, right? If it is a valid solution, the solution is called a certificate. So like a certificate of authenticity, you've got this magic box that says, yes, this is a solution. How did it come up with it? I'm not going to tell you. I'm magic, right? Here is my certificate of authenticity, though. Here is a proof that that solution exists. All right. Overall, a Turing machine, a non-deterministic Turing machine, accepts an input if any possible computational branch or guess is a valid certificate. Right. So now to understand this idea, let's go ahead and revisit. I don't know if we looked at it before, but let's go. You've certainly seen it, say, in 235. Let's go ahead and look at a problem called satisfiability. Satisfiability. Right? So the idea here is that given a logical formula, phi on n inputs. Sorry, I want x. On n variables. The question is, does there exist a truth assignment to x such that phi on x evaluates to true? Okay. So now you've all done this. This is like in the first couple of weeks of a 235 class. Let's go ahead and review that. Here is a satisfiable, or a logical sentence, basically, on three variables. The variables are x1, x2, and x3. Okay. Now let's go ahead and remind ourselves what these symbols mean. What does that mean? That's an OR. That's the logical OR. Right? And that's the logical AND. Right? Now what are these things? That's not. Right? So everything that you've done for programming since day one, right? The logical OR, right? Two Sheffer strokes. The logical AND, ampersand, ampersand. The logical NOT, right? Exclamation point. Or since we've been using Python, what are these?
Or and not.
Or and not. There you go. So it does. I do like that Python uses those keywords instead, but that's one of the few things I like about Python. Right. All right. So there's our reminder. Right. Now, what is the satisfiability problem? Does there exist a truth assignment to those three variables such that this entire thing evaluates to true? Right. So in 235, you do this all the time. You do what's called a truth table. Right. So what values of truth are there? Well, they could all be false. The first two could be false, and the third one would be true. Right. And what pattern am I following here? I'm just counting in binary, exactly. True, true, false, true, true, true. Right? Now, given those three values, do any of these make this entire thing true? Well, help me out here. If they're all false, false or false or false, what's that going to be? False. And because I've got and, do I have to evaluate the rest of it? Nope. Short-circuiting, right? It's easy. It's not just for programming languages. It's also for getting your 235 homework done quickly, right? So false value or result. Okay. Well, what about this other one, 0, 0, 1? Now this is 0, 0, 1. So now this entire thing becomes true. Why? Because this is a disjunction, or. Right? But I've got false or false, not false becomes true. So that becomes true. What about this one? False, and remember that x3 is now 1, and so the negation of that makes it false. And so what happens to this? These are called clauses. What happens to this third clause? It's false. If any one of these clauses is false, then I'm done. All right? False. Okay? So we're kind of brute forcing it here, right? So let's continue here. Well, do we need to continue, or will you believe me that this is not satisfiable? Yeah, it's probably not because I named the file not satisfiable. And then I've got another file in there that is satisfiable that we'll use later on, right? This exact one? Like, you remember these clauses?
It seems familiar because it's like something has to be true and something has to be false, and then all the middle ones are like you can't really have a combination.
Yeah, I don't know. I don't know. I thought I wrote this, but I just tailored it so that it would not never be true.
Yeah, it was at least something similar. I feel like.
Okay. All right. So now let's make some observations here. This problem, is it in P? Is it in EXP? Right? Is satisfiability, and I'll just shorten it to SAT, right? Because that's what it is. In EXP, right? Question mark. Is SAT in P? Right? So what's the answer to the first one?
Yes.
Yes. Why?
So we can generate all.
Generate all possible order to the 2n lines in your truth table and deterministically go through, evaluate each one, and if you ever find one that's 1, you output yes, it is satisfiable. If all of them evaluate to false, then output no. Right? That's pretty clearly exponential, so yes, it's an EXP. Is it in P? We don't know exactly, right? But is it in NP? Okay. So now to understand that, let's go back to our definition here. So something is non-deterministic if it works in 2 phases. Can you guess a solution, right, in polynomial time? Right? I should have written that. You guess a solution to a given problem non-deterministically in polynomial time, right? And then verification also has to be polynomial. Right? Yeah, go ahead.
Like a non-deterministic exponential.
There is, but that's even higher up. That's way beyond. There are. If you go to complexityzoo.com or something like that, you'll find that there are actually hundreds of complexity classes, because this is a big area of research. People come up with, well, here's a problem. Where does it fall? Well, it looks like it's unique. And so let's create a new complexity class to capture the idea, right? And then you can, oh, well, no, it's not actually unique. It falls within this complexity class, but we don't know if it falls in that complexity class, so it's somewhere in between, and we've got something new, right? Or we've got another characterization of a different complexity class. Right? So is it an NP? I'm going to prove that it is by giving you a non-deterministic polynomial time algorithm that decides it. Right? So here's my input. My input is going to be a logical formula on phi x on n variables, x1 through xn. Right? My output will be a yes or no question. Remember, it's a decision problem. Is it in the language or not? I'm not trying to find the best solution, or I'm just trying to find a solution, right? Yes, if there is a truth assignment to x such that phi on x is true. No otherwise. Okay? So here's my guessing phase. Guess values x1 through xn. Right? So now this is non-deterministic because I'm simply guessing the values, and it runs in order n. Why? All you have to do is guess 0 or 1, 0 or 1, 0 or 1. How many times? N times. Okay? That's my first step. 2, verify. Right? Plug in x1 through xn into phi and evaluate. This is going to be at most order n squared. I'm going to be very loose on that. It could be at most n squared because, you know, if just given one of these things here, all you have to do is plug it in here, and there could be many clauses. So each variable could be represented twice by its variable and its negation, and then it could appear in almost like half of the clauses or something like that. And so it would be this, you know, at most n squared, right? So hopefully you buy that at least, and I don't have to go through a detailed analysis on how you can actually evaluate a propositional formula, right? Except if any computation path, or here, let me rewrite that, right? If phi on x is 1, accept, else reject, right? So, I mean, it's pretty straightforward. It's just those two things. You guess, and then you accept or reject. The magic comes in this. Yeah, go ahead.
How do we non-deterministically generate that? Just like, does it matter?
Well, like I said, it's magic. It's a theoretical model of computation. How your question of how do we do this is you don't, because there's no such thing as a real non-deterministic computer. You can simulate non-determinism. And for that, let's go ahead and take a look at let's visualize the non-deterministic computation first, all right? So when we guess x1, let me write it like this. Yeah, x1. You have two guesses. You can either guess 0 for false or 1 for true, right? That leads down two computational paths. The second one, x2, you can guess either 0 or 1. x2, having guessed 1 over here, again, you have two choices, 0 or 1. x3, 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 again, two choices, two choices, two choices, two choices, dot, 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 okay? Down to your final choice, xn, right? xn, right? And you have 0 or 1, 0 or 1. Right? So you've got this big, giant computational tree. First of all, what's the depth of this tree? N. I'll just say order n, right? What is the width of this tree at the bottom? 2 to the n. Why? Because that's how many truth assignments there are, right? Now, each one of these, 0 or 1, you either, question mark here, right? You either accept or reject, okay? Now, that means that you've got an entire row here of 2 to the n possible accepts or rejects. The entire machine here accepts or rejects, accepts if there is at least one path that accepts. Right? So in other words, all of these could reject. But if there's one that accepts, right, then the entire machine ends up accepting. Basically, the magic is that you're able to do this entire truth table in parallel without the actual parallelism, right? You are able to say, okay, well, look at all of these simultaneously, all at the same time, and if there's any one that's one, then we accept, right? It's like one big giant disjunction. This or this or this or this. It is not, don't try to wrap your head around it because it is not a real computational model, right? It is a theoretical model, right? It is something that looks like this, that you are well familiar with, that is easy to understand. There exists an x1, x2, dot, 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 xn, such that phi on x1 through xn evaluates to true. Right? The reason that they came up with the idea of nondeterminism is that they wanted to capture the power of this thing right here. What is this thing right here? There exists. There exists. In other words, it is a existential quantifier. All right? So if you just look at a regular one solution, right? You're just looking at this. But if you want to look at all possible solutions, does there exist a solution? Then you're talking about quantified logic. First order logic, quantified logic. Nondeterminism was designed, where is it? Yeah, nondeterminism was designed to capture this notion of quantified logic, right, in one step. So the depth here, that's your time, right? And this is your quantifier power. Right? So that's what nondeterminism is. Right? Again, it's a theoretical model. Don't try to think of it as real. If you try to think of it as real, you can, but then what road are you going down? Right? Okay, I'm going to try every single possibility. I'm going to brute force this. I'm going to write out the truth table for this thing. Right? How do you go about doing that? You go down one computational path. Oh, that didn't work. You backtrack and go down a different computational path. Oh, that didn't work. You backtrack, go down a different computational path. That didn't work. Backtrack, try another one. That didn't work. Right? So in other words, you end up examining every single possible branch deterministically, right? Which leads you to exponential time. But that does give us our first observation. You can always simulate non-determinism given an exponential amount of time, right? All you need to do is try every single possibility. Now, what is P versus NP? Oops. Versus NP. What's their relation, right? So, my first observation is that, is this true? Any problem that is solvable in polynomial time, is it also solvable in non-deterministic polynomial time? Yeah. What do? You just don't guess, right? You solve it. Then you don't need to verify at all, right? So, there's my second observation. That gives me a landscape of problems that we've seen so far, okay? Here's, yeah, there we go, cool. It'll do parabolas like that. Yeah, go ahead.
Looking at it non-deterministically
Mm-hmm.
means that you just look at them all at the same time.
You have this magic power
Okay.
to look at all solutions at the same time, right? But the resource is still constrained by your guessing phase, right? I was able to guess all the solutions in linear time, in polynomial time. But the guessing and looking at all of them at the same time, that's the power of non-determinism, right? That's the magic power, right? So, exp, come on, there we go, NP and P. There we go. This is the landscape that I've got so far. This is basically a Venn diagram. It's just a different way of writing it, right? So we've seen problems that are in exponential time and non-deterministic polynomial time and polynomial time. For example, sorting, right? What about a graph problem that's in P? Shortest path? And, well, technically shortest path is a optimization problem, right? We took care of that technicality, if you remember, by changing the problem to a decision problem. That instead of asking what's the shortest path from X to Y, you ask, is the shortest path from X to Y, the next vertex would be Z, right? And the answer is, well, yes or no, right? And so then you can build the path along by asking those questions over and over again, right? So it's still going to be in polynomial time here. It's just that you have to be careful because you need a decision version of that problem. What's something that's in NP? Well, we just saw SAT, What's something in exponential time, but that's not in NP? I don't remember anything off the top of my head that's a natural problem. I think Go. Do you know the game Go? No, that'd be P space. I forget. Anyway, there's some games that you can come up with that are provably exponential time, but non-deterministic polynomial time. I'm not sure, but I'll go ahead and leave this as a question mark, and maybe come back with another example next time. But there's our landscape so far. The P versus NP question is, we know that P is a subset of NP, but is the other way around true? Is P equal to NP or not? Right? That's the question. Right? In other words, do these two things, do they actually collapse down? And P is equal to NP. These very, very difficult problems, right? Like SAT or 0-1 knapsack or Hamiltonian path, right? 0-1 knapsack as a preview here, knapsack, ham path, right? Those are problems that are in NP. Right? It's very easy to show that they're in NP. All you have to do is come up with a guess and verify algorithm to do so. Hamiltonian path, guess a path, verify the path, right? And you've shown that it's in polynomial time, and that guessing phase means that you are using nondeterminism, and therefore it is in NP, right? Well, certainly NP is going to be in exponential time. But what I want to do is I want to focus just on these two, right? How do we go about answering this question? To do that, what we need to do is we need a new tool, right? To begin to answer P equal to NP, you need a tool to compare problems. This is where the difference between problems and algorithms comes in, right? To compare algorithms, what tool do we have? To compare algorithms, such as, say, selection sort and quicksort, we have a tool called big O analysis, right? Order n squared and order n log n. Right? Right? Big O. Algorithm analysis is our tool. All right? But do we have a tool to compare problems? For example, is shortest path harder or easier or the same as Hamiltonian path? We do remember what Hamiltonian path is, right? Given a graph G, you want does there exist a path that visits every vertex exactly once? Hamiltonian cycle, does there exist a cycle that visits every vertex exactly once and returns back to the original vertex, right? Shortest path here, given two vertices, does there exist a path from one to the other, right? So is this one harder or easier or the same as this one? Right? So that's where we need a new tool. That new tool is called a reduction, right? To compare problems, right? You may not even have an algorithm for it, by the way, right? So if we had not looked at Dijkstra's algorithm, right? If we had not looked at the brute force solution for Hamiltonian path, we might live in a world where we don't even know if there is an algorithm at all, right? So in fact, take all that knowledge out of your head of what the algorithms are and throw that out. I still want a way to compare these two problems, right? So to compare problems, not algorithms, you need what are called reductions. Right? A reduction is basically a mapping from one problem to another problem, right? What this is A and B are problems. Or in our mathematical language, they are languages. Right? Less than or equal to P means that A reduces to B. Right? There is a relationship here. A is, I don't want to say it's easier, but it is no harder or no more complex than B, right? Another way of seeing this is that B is at least as complex or hard, difficult as A. Now, why did I use that imprecise language? Did I say that it's actually harder? No, because these are just two relative measures. That's why we say less than or equal to, right? 5 is less than or equal to 6. That's true, right? But 6 is provably more. But it's also the case that 5 is less than or equal to 5, right? But they're the same, right? But just saying that A is less than or equal to B leaves open the possibility that they could be equal, right? That's exactly what we want here. This is at least as hard as this down here. But do we know whether or not they're equal? Not yet. That's $1 million question. Right? Literally $1 million question, because the Clay Mathematics Institute has offered for the last 20 years $1 million prize to anybody that solves it. Right? It's one of the 7 millennium problems. Yeah.
Solve if P is equal to M.
Yeah. I mean, I think that they didn't really phrase it correctly, because I think that they asked for one solution, that they have to show that it's not equal, because that's what everybody believes. But what if somebody does come up and say, well, I've proven that they're equal? They should still get the $1 million. But according to the letter of what their call is, they're not asking for that. But no, I'm sure that they would still give out the $1 million. The $1 million prize is ancillary to the fame that you would get for actually solving this problem. But anyway, it's a relative comparison between two problems. And now, sorry for the last 5 minutes here. Here's my rant on what it means for two reduction. We haven't defined reductions yet. We'll do that next time. But here's the idea of a reduction, right? You're taking problem A and you're reducing it to problem B, right? Now, this is more complex, and this is less complex or difficult. Difficult. Because of the way that I wrote my landscape here, right? That say that this is P and this is NP. Okay? So when I say that something is being reduced, A is less than or equal to P, and again, we'll define that later next time, then basically I'm increasing the complexity. That doesn't, here's my rant. That doesn't sound like a reduction to me, right? If you're reducing something, you are reducing its complexity, but that's not what it is, right?
Make the problem simpler.
Yeah, you're making it simpler. Exactly. That's exactly what a reduction is if you're cooking, right? If you've ever made a reduction, or I don't know if anybody cooks for themselves or not, but you're basically boiling off the water so that you can concentrate the flavor, right? You are doing a reduction. You are simplifying it down to just the non-water components, right? That's what reduction means to me. Or you're reducing the problem, you're reducing the amount of work, right, et cetera. I've never been able to find a satisfactory answer to why they called it a reduction, right? The simplest way that I've been able to wrap my head around why they use that terminology is because, well, to solve this problem, all you have to do is solve this problem. So I've reduced it down to a simpler problem, or I've reduced it down to a simpler task, a different task. And that's the idea here, right? Because basically, if you have a problem A that you don't know how to solve, right? And you've got a problem B that you do know how to resolve, well, now you have solved A. By taking A and transforming it into a problem B, applying that problem, that solution, that algorithm to that problem, then you've ultimately solved the original problem, right? We'll see. We'll start tomorrow or Wednesday's discussion on very practical examples, right? You do this all the time. You just don't call it reductions, right? You write functions, right? If you want to write a function to, like, I don't know how to solve this problem, but there's a function over there that does it for me, but I just need to tweak the input a little bit in order to get that function to work, right? That's a reduction. That's what you do all the time in programming. You don't rewrite things from scratch from the very beginning. You reuse these functions over here. So if you've got a problem, all you need to do is reduce it to this other problem, apply that solution that you already have off the shelf, and you're done. Right? We'll see 3 very practical examples next time. Okay. In fact, I'll bring in Network X in order to demonstrate it. Right. And the stuff that you've worked with before. But there ends my rant. Don't ask me why they call it reduction. That's just what it is. Understand that it goes against every intuition that I have about the meaning of the word reduction. And so I don't know. If you have a different intuition, tell me what your intuition is, because I'd really like to know why they call it a reduction. Right? You're not reducing anything. You're making it basically more complex. Right? Ultimately, what we're going to do is we're going to take problems and we're going to reduce it down to what these things called NP-complete problems, right? And then every NP-complete problem reduces back down to itself, right? So that's how we're going to ultimately classify all these problems between P and NP-complete, and then is there anything actually in between? And the answer is yes, but it's not natural. All right. So we'll pick it up there on Wednesday.
So in my